Thanks, Mike, for the introduction. Good morning, everyone. As you can see, the topic of my discussion for the next 30 minutes is going to be, will everything start to look like an SoC? I think the question is, will SoC have the same kind of challenges that we have seen with the growing design size, or are these challenges going to be different? Mm-hmm. Okay, so before I go into the SoC, let's look at the current landscape. I think we must admit that SystemVerilog has inherited the earth. It may or may not be the best language for verification today, but clearly it offers a lot of possibilities and opportunities to the verification world. SystemVerilog and UVM are mainstream. I think there may be other languages that may offer better syntax to do verification, but I think looking at the adoption of both the language and the methodology, I think they are the mainstream language and methodology today for verification. While the language and methodology gets adopted, at the same time, the previous languages and methodologies will continue to exist for legacy reasons, especially for the organizations that have a lot of legacy code. They may continue to persist with those kind of environments. But at the same time, the new developments will be slow in those methodologies and languages, and the new users or the new adoption will be less and less. So what SystemVerilog really enables is a methodology development ecosystem. This is the ecosystem that you need to deal with some of the verification challenges of today's SoCs. You need verification planning so that you can specify your requirements. You can specify what you want to test and what you want to track. You need verification management to track your verification over a period of time, to track the trends, to track the progress of your verification. The methodology also enables technologies like constraint solver that help you go ahead with the constraint random methodology and uncover bugs as part of verification. You need template generators. These are essentially executable specifications. I think a good example of an executable specification is your register specification. I think most of the organizations have some kind of a documentation on registers. I think what these template generators offer you is essentially a way to create an executable specification based on the register description of the specific design that you want to verify. At the same time, the language needs to connect with or coexist with some of the other languages with similar semantics. Good example is SystemC or C++. So UVM TLM 2.0 offers adapters that allow you to connect your UVM-based verification environment with the languages with similar semantics. You need UVM AMS. Essentially, this is for verifying your analog mixed signal designs. So at Synopsys, we have created utilities on top of UVM that lets you adopt constraint random methodology for analog mixed signal designs. It lets you decide which transactions to randomize. It lets you decide what do you want to cover in an analog mixed signal design. Debug, I think that's the most important piece here. UVM, if you look at, it's a set of class libraries, and it's essentially to be seen as a language on top of SystemVerilog. So when you're debugging, you don't want to be debugging by stepping into the UVM class libraries. You need some kind of a infrastructure that allows you to debug more at UVM objects level. Right? You want to be debugging more in terms of agents and environments and TLM ports, rather than having to step through some of the UVM classes. UVM also enables VIPs, so it defines how VIPs need to be developed for verification. So some of the VIPs, and I'm going to talk more about it in the subsequent slides. Essentially, it helps you define how VIPs need to be developed for constrained, random, and coverage-driven verification. So speaking about debug, the debug needs to be at a more protocol level, where instead of having to deal with various layers inside the VIPs or the signals at physical level, what you need is essentially debugging at protocol level, where you are dealing with transactions, transfers, you're dealing with bus accesses, rather than having to worry about how these are implemented inside VIPs at lower levels. And lastly, all of this gets tied in through coverage analysis. I think the coverage analysis, as we all know, it's very important to help track what is covered and the parts that are yet to be covered. It helps you decide your further strategy on hitting the holes in the verification. So coming back to the topic of my talk, will everything start looking like an SoC? If you look at the domains today, I think we can broadly divide them into two parts, mobile and processor. I know there's a third domain, which is network processors, and I think they were already using SoC-like styles I think some time back. But I think if you today's world, if you look at it, broadly divided into mobile and processors. At mobile, your focus is more on how to optimize power, how to have support for external standards, because your mobile devices need to work around the world. They need to connect with different protocols. At the same time, you need to have good capabilities of graphics processing, because your user experience is directly dependent on your ability to process graphics and video. The software content is exploding definitely here. I think there's an enormous amount of software that you have to deal with, and also there are links to analog. Essentially, we're talking about links to radio as part of your mobile device. On the processor side, the focus has been on high performance, improving your internal architecture to deliver the same. Your data processing should have to deal with much more amount of bytes you can push, and also the software. I think when it comes to software, the focus essentially is on the backward compatibility. Whether the new software, whether the opcodes are backward compatible, so that your software continues to run on the newer versions of the processor. Now, with the coming of SoC, these two words are kind of merging. Right? It's no longer just performance or low power. Right? I think you need to have a trade-off between the two. Similarly, you need to take care of both internal and external standards. Even in case of processor, you need to worry about external standards because you need to connect with memory models or cache coherence buses. Similarly, links to analog, multiple processors, multiple protocols, all that need to be taken care in the context of SoCs. Now, what this does is the SoC, the design styles or what you do, it starts applying across wide range of applications, ranging from automotive and industrial to all the way to military infrastructure and scientific applications. Now, the advantage clearly is the tools that you develop for SoC are going to benefit all kinds of chip designs. At the same time, clearly the convergence is what is driving the SoC complexity. I think it is the convergence of PC and mobile leading to increase in the features on your SoC. So this platform convergence is the key driver behind SoCs of today, and we're clearly seeing the increase in complexities of specs. The specs are difficult to write. Sometimes they are difficult to interpret. The time to market is clearly shrinking. I think there's clearly pressure on to deliver, sometimes even deliver before you are even done with verification. So clearly, I think time to market is critical. I think you look at the example of smartphones. I think here the top two players are, I think, Apple and Samsung, who dominate the field, and the remaining if you look at the remaining segment, I think the players are just have to deal with the fraction of the market. So clearly number one and number two makes most of the money right in this segment. There's an exploding software content. It is not the software that you just test as part of your SoC. There's a lot of software that gets offered through application centers where you don't have any control on. I mean, a very good example is I think the software that you get for Apple, the apps that you get for Apple or Android applications. And so I think when you are doing a verification, you have to keep in mind the software that gets used is going to come from all kinds of sources. And this is all leading to increased development costs. Right? Essentially, you're going to lower nodes, your cost of hardware is increasing. At the same time, there's a lot of stress on the hardware needed to verify these designs, right? Whether it is the compute infrastructure, the disk space. So all this is leading to increasing development cost. Now at Synopsys, we track all the leading designs in the industry, and we track some of these metrics. And here's an example of one of the largest designs that we dealt with in recent times. And this kind of help you understand the verification complexity of today. If you look at the number of lines of code that you need to compile, the tools of today that need to compile is around 50 million. Right? This is the lines of RTL and test bench. The memory required to be able to simulate such a design is almost reaching 200 gigabytes. So this is what I'm talking about in a full gate level, full timing gate level simulation. These designs have more than 10 protocols. They generate terabytes of coverage data. So it's no longer feasible to have your simulation run in one part of the world and then you expect all the coverage data to be residing locally on your desktop. You are talking about a completely different hardware infrastructure to deal with such a kind of verification complexity. This design has 300,000 plus assertions. So as you can guess, most of them could be machine generated assertions. 200 plus power domains. Each power domain has certain IPs inside it, and you need to make sure your IP gets verified in the context of these power domains. Debug, I think I say is 35% of verification, but I think these days when I speak to some of the verification groups, clearly we hear numbers all the way up till 50%. I think it depends on what you talk as debug. I think any design activity today, more or less, is more likely a debug activity. So it's very important. Clearly, the investment in verification is twice as the investment in design. And as I spoke about, the hardware infrastructure that you need to be able to verify such a complex design, right? I mean, that's growing at multiple times, and that is also leading to increase in overall development cost. So what you essentially need today is 10x increase in overall productivity of verification. Now, to enable such a productivity, the innovation around tools and technologies needs to be accelerated. So clearly, you are looking for tools and methodologies that help you get an order of magnitude of performance, that give you a capacity to be able to accommodate designs that I just described. You're looking for verification IP productivity, again, which is 10x. Similarly, constraints and coverage. You're looking for low power solutions which are advanced, which can deal with some of the latest low power verification techniques, and at the same time deal with the complex designs of today. Similarly, I think if you see, the performance continues to be one of the key areas of focus, whether it's high-speed AMS simulation. And then your debug productivity, that's where you engineers spend most of the time, right? So that needs to again go up by an order of magnitude to be able to not only uncover bugs, to be able to resolve all the issues and meet your time to market. The reuse methodology also needs to undergo change to be able to deliver this 10x productivity that we're talking about. And similarly, there are requirements on hardware and software co-verification. So I'm going to dwell upon some of these areas of innovation in the subsequent slides. Let's start with 10x performance and 10x capacity. So if you look at some of the hardware of today, I think there is massive parallelism that's available. If you look at the processor designs are no longer focusing on gigaflops or MEPS. I think they are looking at how to bring in inside the chip. This more power, one way to add more power is to put in more cores, and that allows you to, I think, enrich, bring in more features. So a good example is some of the processors of today. I mean, it's very common to see processors which have 4 cores, 8 cores, or 16 cores. Those kind of hardware is available and used for development. So there is an opportunity to parallelize inherently the designs for verification. If you go at lower level of parallelism, you could be looking at 160-bit adders, 64-bit adders, 100 plus. So that gives you an opportunity of parallelism at lower level. Other way to look at parallelism is your regression suite. You're looking at running your tests on the same day. You have thousands of tests that you want to run on your same design. So there's an opportunity of parallelism there in a sense. Think of a single instruction, multiple data, a kind of a model. So imagine if you had a way where your overall regression throughput improves by an order of magnitude at the expense of increasing your test runtime a little bit. So that's another opportunity, and but at Synopsys we have had this technology that we have deployed at customers where we have been able to improve the overall regression throughput using a similar methodology. Now, new compute forms do offer, I think, opportunity to improve simulation. And I think the excellent example is, look at CPUs of today. There is a GPU sitting next to each CPU. I think that gives you enormous compute power that can be used to deliver high simulation performance. So to think of, I think you could have your RTL instead of running on CPU, it could be leveraging the GPU cores that are sitting on the next to the CPU. Similarly, you could use FPGAs for acceleration. This is different from traditional usage of FPGAs where you wait for an RTL to mature and then you take your RTL to FPGAs. Here we're talking about accelerating your RTL while it is getting developed and reducing your overall development time. So I spoke about VIP productivity as another challenge. I think if you look at the picture today, this is the reality. I think you have so many protocols, and it's not just these protocols. Each protocol is also undergoing revisions. And if you look at each of these revisions, sometimes are as good as a new protocol. And I'll show you an example in the next slide. So essentially, you are talking about more protocols per chip, and essentially each protocol is evolving. Here's an example. Sometimes, I think an example of USB 2. I think the difference between the USB 2 and USB 3 standard, if you look at, the complexity has increased so much that you're talking about 20 times more scenarios, and you are having to deal with 10 times more data here. So essentially, that was my point when I said it's not always the new protocol. Sometimes the revision itself it leads to a standard which is as good as having to deal with a new and lot more complex standard. So essentially, if you look at 15 years back or so, your VIPs were primarily used for block level or IP level verification, and the way your VIPs were built was layers and layers of language and methodology as these languages and methodologies were getting evolved. And what you had was almost like a Frankenstein kind of a VIP that you have to deal with its inherent limitations in terms of performance and debug. So essentially, with the advent of SystemVerilog, what has happened is now you have a single language that can be used to describe your complete VIP. What it does is it helps you deliver the required performance because now your VIPs are natively compiled in whatever simulator you might be using, SystemVerilog simulator you might be using. And the methodology, the UVM methodology with VIP has enabled ease of use. The methodology itself is natively supported with the VIP. These VIPs come with collections of sequences. So you can pick up sequences based on the kind of test you want to generate or the kind of holes you want to plug in your verification. They come with built-in coverage plans or coverage models. And at the same time, each of these VIPs enable what's called as protocol-aware debug. What essentially means is you are debugging more at the level of verification. You're debugging at the level of the transfers and accesses that you're trying to simulate and verify rather than debugging at signal level. Then I spoke about 10x improvement in constraints and coverage efficiency. So essentially we are talking about interactive constraint random verification here. It's not just about generating constraint random tests, hitting cover points. It's essentially about, does it make sense to reach 100% coverage goal? Are there cover points that may not be reachable? So you need tools to come back and tell you that in your coverage plan, you have specified certain points which are absolutely not reachable, and it's better for you not to spend or reachable cover points that you can go back and analyze and take a decision whether these points are truly unreachable or there is or you need to go back and rewrite your constraints. So essentially, again, at Synopsys, we have been working on some of these technologies, and we have had people that have used successfully in their design projects where they have been able to improve the overall constraint random verification time using some of these tools. Low power is very key. I think most of the SoCs have goals on low power. I think what capabilities of low power verification natively built inside your simulator. It doesn't have to be a separate tool that interfaces with your simulator. So essentially, your simulator should be able to offer you a unique voltage-aware modeling engine, and that in turn has benefits of delivering performance and also providing the capacity to handle designs of today. So essentially, as an example, the VCS has UPF modeling capabilities built natively inside it. What it actually, some of the numbers that we have seen, what it gives you is 50% faster and higher capacity than a non-native or a PLI-based solution. The use model is very simple. I think it's as simple as just specifying a dash UPF switch and you're ready to run your UPF simulations. At the same time, you can run your low power verification along with your test bench coverage and debug. So it's all a single compiled step, and you can track your low power just like you track your test bench verification. At the same time, you need capabilities in debug to be able to look at a low power more from a verification point of view. Right? So it should be able to show you the interesting low power features as part of the overall debug capabilities. Debug, as I said, I believe it's the most important aspect of verification today. And in fact, that was the reason why we acquired Wordy technology a few months back. I think the most important, one of the most important aspects in debug is, I think the debug that you should offer should be methodology aware. Right? It should be able to hide the unnecessary details and provide you enough level of abstraction at a level of the methodology. If you take an example of UVM, you should be debugging more at agents and environments and TLM ports level rather than debugging at class level. Similarly, there are other capabilities like ability to record transactions, ability to go back and replay those transactions. Protocol-aware debug, you should be, for example, able to look at through a debug tool how your USB transfers are resulting into NAX, IXS over a period of time. Should be able to go back in time and look at some of those transactions and then be able to debug your verification. This has been a dream of right, every verification project. Right? Essentially, you want to be able to detect your bugs as early as possible. Right? I mean, this ties into the goal of bug avoidance. I'm going to talk about a couple of technologies here. I think one is essentially have to do with using C reference model as part of your RTL verification. So think of it, you made some tweaks in your RTL model, and then you go back and tweak your C model to reflect the same changes. So instead of having to run long RTL or complex RTL simulations, what I think would work or what would be more productive is to do an equivalence check between the C and the RTL model and make sure both are actually representing the same functionality. So this is what the Hector technology is all about. It's essentially an equivalence checking tool that allows you to verify C2C or C2RTL models. Talking about gate level simulation, I think one of the reasons we do gate level simulation is to catch X-related bugs, right, or X propagation. And we know gate level simulations are very expensive, more in both in terms of runtime as well as the hardware cost that comes along with. I gave you an example of one such case. So essentially, what you need is be able to catch these X-related bugs at RTL. So X propagation technology that I speak about here, what it does is it tries to overcome some of the limitations in RTL that prevent X propagation and brings in the semantics right at RTL level that allows you to detect these X-related bugs. So essentially, you can detect most of your or all of your gate X-related bugs at RTL level using X propagation. So so now going forward, right? Look at how did we deliver or how did we come up with some of these interesting technologies? It was not possible to just develop them in isolation. This was all possible as a result of a long partnership with various design and verification groups, right? And again, I think we have some of the examples here. I think if you have specific verification challenges, if you have specific SoC related issues that you would like to discuss with Synopsys, that you would like us to solve, I would encourage you to come forward, partner with Synopsys. You may already have a partial solution that deals with your problem, and then we can work towards delivering a complete solution that will help you meet your SoC verification challenge. Yeah, with this, I will complete my talk. Thanks.
Hello. We do have some time now for questions for Vikas, if there's any questions from the audience at all on any of the points that were covered in that. I personally think it's a very excellent introduction to the conference today. I think the themes there seem to be challenges. We all know we've got a lot of challenges. The variety of solutions that you need to apply to those, and the theme of partnership, which we finished on. And these solutions are much, much better developed in partnership rather than in isolation. So I'd like to thank Vikas for such an excellent introduction. If there's any questions at all. One question. Okay, I'll come to you with a mic. We do, just for the record, we have about 300 people online, so if you ask a question, we need to pass you the mic.
You started with the thought, will everything start to look like an SoC? Looks like the answer is yes, after going through your presentation. Two questions, what next? And the second question is, if it starts to look like an SoC, like, where is it converging towards?
Okay, I think a good question. So I guess when you say what next after SoC, are you talking about the design evolution, or are you talking about more in terms of, okay, everything looks like an SoC, now we as verification engineers, what do we do with it? Is that your question?
Yeah, right.
Yeah. So clearly, I think if I look at the extreme end of the SoC complexity, I think one of the challenges that SoC designers face today is verification. I think it's not the ability to design SoCs. It is essentially the ability to verify SoCs that are essentially driving the kind of SoCs you can deliver. So verification certainly is becoming the heart of the kind of SoCs that you can design, the kind of applications that you can target. And by the way, this is something that our customers have told to us, that I think there have been instances where a design had to be called off because it was not practically feasible to verify it within the time window that was specified.
That's a very interesting topic. With a lot of our clients, we work on design for verification. We've had design for test for a long time, but I think design for verification will actually become more and more important, and be able to come up with designs that are actually verifiable rather than.
Exactly.
Okay, so thank you very much.
Thank you.